We will go through one more example pertaining to spherical polar coordinates. Here let us take up something little more complicated than the previous one. So, this is the object we are going to consider. It is in the first octant, and this is where it touches the xy plane, this is where it touches xz plane, the plane closest to us. The charge density of this object is given by this. Now, the problem is, even though it is given in x and y, the object is a portion of a sphere. Therefore, we cannot use rectangular coordinate system here in this case. Therefore, we will try with spherical polar coordinate system. To do that, first we need to find we need to find the total charge, right. So, first we try to invoke the infinitesimal volume element. It is this one. We went through that in the earlier problem as well. Now, we need to figure out the limits of these three variables. Now, you can see that with this object, the closest surface is r1 units away from the origin. The furthest surface is r2 units away from the origin. Therefore, r goes from r1 to r2, right. So, this is what I have indicated here. Now, the angle phi, right, phi is the angle that makes any line segment connecting the origin and a point in this object with z axis. So, that goes from 0 to 90, because the entire object is in the first octant. Therefore, phi goes from 0 to 90 degrees, so 5/2 radians. Now, theta is this. When you project this onto xy plane, the angle between the projection and the positive direction of x axis, again the angle theta here is the line of is the angle between the line of projection and the positive direction of x axis. Now, you can see that that goes from 0 to 90 as well. So, that I have indicated here. We are going to use this in future. Now, charge density is given like this. Now, again this is in rectangular coordinate system. So, we have a little problem when we are dealing with a rectangular coordinate system here, because the object is a portion of a sphere. Therefore, we have to convert this into spherical polar coordinates. Again, we will go back to the previous definition. Now, if you take any point here, point P, the line segment connecting the origin O and P is a length of r. Now, when you project it, you get this as r sin phi. So, that is OQ. So, OX gives you the x coordinate, which is OQ cos theta. You plug in this and you will end up with this result. Similarly, to find this line segment, which is y, which gives you the y coordinate, is OQ sin theta. Again, you will end up with r sin phi sin theta. Now, when we use these two to find the charge density in spherical polar coordinates, you can plug in these. You can see that r squared sin squared phi is common. You pull it out, you will end up with cos squared theta plus sin squared theta in the parentheses, which is 1. So you get the square root of this. Remember, the square root is always positive, so you need to justify that this is non-negative. I mean, square root should be non-negative. So we need to justify that this is non-negative. So r is greater than 0, and since phi is in this range, we know that from 0 to pi, sin phi is non-negative. Therefore, it's okay. Now the charge in the infinitesimal volume element should be the charge density times the volume of the infinitesimal element. So the product of these two gives you the charge in the infinitesimal volume element. Now, to find the total charge, you have to integrate this infinitesimal charge in the volume V. So this is the infinitesimal charge. So you integrate it, you get the summation in volume V. So you keep this intact. Now recall those limits. Again, I will go back there. These are the limits of the respective variables. Now you assign those respective limits in the appropriate places. Now, here in the first case, just for the sake of clarity, I will put a pair of braces, and remember that it is not a must, but for the sake of clarity, if you want, you can introduce a pair of braces like this. Now, when you integrate this, you know the variable of integration is r. So it will give you r cube over 3. Remember, in multiple integrals, always the other variables are treated as constants. Therefore, here sin squared phi is treated as a constant. Therefore, you simply integrate this one and you will end up with r cube over 3. Now, plug in the respective limits. So first you substitute this one. Again, you keep these two intact. Plug in this one. So r2 cube minus r1 cube over 3. You keep this sin squared phi intact, right? That's how you connect this line. I mean, that's how you go from here to here. Now, once we come up with this line, now we have already simplified a triple integral into a double integral. Now our life is little easier with this point onwards. Now from this point onwards, now you pull this out, you keep these two, right? Now the variable of integration is phi. Now sin squared phi cannot be integrated directly. Therefore, you have to use that double angle formula, reverse of double angle formula, and you know that sin squared phi can be expressed by or expressed in terms of cos 2 theta in this way. So sin squared phi was replaced by this one. Now, here there are two terms, you pull these two out, it is easier for us. Then once you pull this out, you will end up with 1 minus cos 2 phi. Now, when you integrate that, 1 gives you phi, cos 2 phi gives you sin 2 phi over 2. Now, you plug in the limits. Here, this is what you get. When you plug in phi by 2, here you get phi by 2, but when you plug in phi by 2 in the second term, you get sin phi, which is 0. Therefore, when you plug in phi by 2, pi by 2 here, you get 0 for this for this one. Similarly, when you plug in 0 in this expression, again you will get 0. Therefore, this will not produce any useful result here. Therefore, when you plug in phi by 2, you get phi by 2 minus 0. So once you deal with these limits, you will end up with pi by 2. Now, it is a simple integral. Now, the life is so easy after this. Now, when you integrate this one, you get pi by 2 times theta, because this is a constant. Now, limits are from 0 to pi by 2. Again, you plug in them, then simplify. These two will give you pi squared. Here you have r2 cube minus r1 cube. The numbers in the denominator, there are 3 numbers, 6 times 2 times 2 will give you 24. So, now you introduce the unit. So, this is in coulombs, therefore, I put a C. All right. Thank you.